Okay, so let's go over some of the equations that we know. Some obvious ones to some more single-use kind of unitasker kind of questions, unitasker kind of equations. So what are some equations you know are going to be on this exam? Let's dump your brain out right now. Anyone know what that equals? K-cat times E total?
Emacs.
Yay! Definitely on this exam. I'll owe you all money if I don't put that on the exam. Okay. So let's look more carefully at this. What does that mean? We can throw up equations all day long and write them up, but you got to understand what they're used for. Why do we care? What's that? Okay, so this is the maximum velocity an enzyme can ever achieve. Dom? Sure, right? So if imagine you have a factory that's turning out something like, I don't know, lumber or something. You got a lot of machines that are cutting up the trees, but they could be old crappy machines, right? Or they could be brand new, really efficient machines. And so the more machines you got that are more efficient, the faster the factory is going to put out lumber. Right? Same thing with enzymes. It's really no different, right? The more enzymes you got and the more efficient they are, the more stuff you can make, right? They're literally the same thing, okay? So we would use an equation like this to solve usually for a K-cat. Typically, we can measure Vmax from a Lineweaver-Burke. And usually we would know how much enzyme we put in the system because we set it up, right? Lineweaver-Burke, which is the double reciprocal plot.
Oh.
This thing.
Okay.
Where does the Vmax show up in a Lineweaver-Burke?
Y-intercept.
Okay, y-intercept is
Vmax
1 over b is equal to Vmax. Or it can be from the slope. Remember, Km over Vmax is our slope. So you can find it in two different places. As long as you know Km, you can get it from the slope. As long as you know the y-intercept, you can get it from there. So typically, this is used in this direction. You can measure Vmax from a Lineweaver-Burke. You know how much enzyme you put into the reaction to begin with, and then you would solve K-cat. Yeah, Sydney. 1 over b, so we would have some equation y equals mx plus b from this. And the b is the y-intercept, and you can just take 1 over the y-intercept to get the Vmax. Right, because this y-intercept, b, is equal to 1 over Vmax. And m is equal to Km over Vmax. What's that? The other intercept is the x-intercept, which is negative 1 over Km. But that's only when y equals 0. Okay, so this is a very common equation, and it's one of the most commonly forgotten ones by students traditionally year after year. People always leave this one out. Okay, does that make sense? Okay, what other ones do you know are going to be on the exam? Okay. Do you guys remember what this one does? What's the use for this equation? What? Concentration of what? Not necessarily. Because enzymes really don't ever show up in the Q here, right? They're catalysts. Q is products over reactants, right? But not at equilibrium. So this tells us, again, real behavior. Remember, delta G is real stuff, given real conditions. Q and T. And we would for example, no delta G, because there's a couple ways we can figure that out. Right, both of those can fit in here in delta G naught. If I know KEQ, I can figure out delta G naught, and then I can plug in my real conditions to figure out the actual behavior of the reaction. Does it go to products or reactants or stay at equilibrium? Q or T.
Oh.
It's not Q over T.
Oh.
So there's like 4 of our equations thrown up there, right? This one allows us to know, essentially it's a switch of terms from equilibrium concentrations into energy terms. This one is enthalpy and entropy combining to make free energy. Right, so both of those go into theoretical behavior of the system, and this accounts for the real behavior of the system. And then for any of these delta G's, any delta G could also be a delta G naught double dagger, right? All these same delta G equations work for double daggers. It's the same kind of thing. It's a generic delta G naught. So for example, if I knew delta G double dagger and I knew delta G naught double dagger, I could figure out stuff from that, I guess, if you wanted to, right? If you needed to. What else? What else you know is going to be on this exam?
The velocity initial equals Vmax times S over
It's just a fraction bound for the enzyme. It's S over Km plus S. Remember that Km here is our binding affinity for the substrate by the enzyme. Yep, by the enzyme. And then Vmax we talked about up here, right? So a question could be, you could use this top part and then plug it in here and figure out velocity at any given point. This whole thing is the fraction bound for the enzyme. Just like H over Ka plus H. Just like S over, or ligand over Kd plus ligand. This whole thing is always a fraction bound in this form.
fraction bound by the enzyme?
Yes. So however much bound we are, that's going to tell us what percent of Vmax we can achieve. If we're half bound, we only get half Vmax. Right? If we're 95% bound, we get 95% of Vmax. It's really as easy as that. What are the variables here? What are the things we can actually change? Concentration substrate, right? We set that up. We can also change Vmax through E total. But Km and Kcat are pretty much set in stone for enzymes. Remember that. So I guess that would take us to our next little equation. What does Kcat over Km tell us?
Efficiency.
Yep. And then what are the units for that? If I want it, okay. 1 per molar per second. So Km has, Kcat's always in per second. Km has to be in molar here. Closely related to that is Kcat over K uncat. What is that?
That's KDQ.
Nope. What's that? Okay. That has a delta delta G naught double dagger in it somewhere.
Oh, is it negative?
E to the? You're getting close. Let's keep
Divided
deck
by RT.
over RT. And it needs to be negative. Because remember, delta delta G naught double daggers are always negative for enzymes. There's never an enzyme that makes things worse, because that would be defeating the purpose of being an enzyme, right? Yep. This is the change in delta G for the transition state between the catalyzed and uncatalyzed state. So if we had an enzyme like this, so this would be our minus enzyme, this would be our plus enzyme. Each of these is going to have a delta G naught double dagger. This is for the uncatalyzed. This is for the catalyzed. And the difference between them is the delta delta G, the change in delta G for the transition state. It does. You got to delta delta it. Hold on, I got Sydney first. Yep. Sure. Yep. So I could write something like this: delta delta G naught double dagger is equal to delta delta H naught double dagger minus T delta delta S naught double dagger. Totally. You have to be consistent with it. You can't make this delta delta G naught double dagger and make this delta H and then T delta S double dagger. Right? It has to be all the same stuff all the way through. Okay, Taylor.
So why are we, isn't the delta G not, does it have, I guess I'm just confused because in previous units that was just delta G, but now it's delta G naught. I mean, delta G naught double dagger.
Uh-huh. What? What do you mean?
So we used to, it was only delta G.
Back in the old days?
Yeah.
So like, is this what you're asking about?
Yeah.
Why is it, what is this versus this? Is that what,
Transition
okay, so the transition state would be going upwards.
yeah.
Delta G could also be, delta G naught could be going downwards or upwards, but it's really the difference between products and reactants,
Oh, yes.
right?
Yes.
Delta G naught is only products versus reactants, right? It's only based on what KEQ,
Okay.
right? Delta G naught double dagger is the change in energy up to the top of the mountain, right? This can never change, right? Every reaction has one KEQ value at a given temperature and only one delta G naught delta G naught value at that temperature. This can change based on the catalyst, the height to the top of the transition state, right? So every reaction has this set. Delta G naught double dagger is not necessarily set depending on the catalyst you're using, right? And the amount you can change that means you go faster and faster, and that's why this is known as rate acceleration. So I could ask you, what's the acceleration of this enzyme if it lowers the transition state 10 kcals per mole? You could say this goes 29,000 times faster, or whatever you say, doing the math.
Because if it lowered it by that much, that would be delta G.
That's going to be, kcat's going to be then a larger value. The lower it is, remember, the higher the hump, the smaller k is, because you can get fewer things over the tall hump. When it's lower, you can get more things over it, and so it's a larger value for k cat, a smaller value for k uncat, and therefore this number should always be greater than 1 for an enzyme.
If you said, what is the acceleration if this enzyme lowered the delta G transition state of 12 kcal per mole and 12 is delta G?
It'd be negative 12 would be the delta delta G because it lowers it, right? And then you plug in negative 12 divided by RT. E to that would be your acceleration factor.
Okay. An enzyme would never slow it.
No, that defeats the purpose. If you're ever slower, then it's just going to go at the free solution rate, which is the rate loss.
Yeah.
It's just going to go back to default, which is reacting in free solution.
Okay.
Heck yeah. You could find this based on solving kcat and, whoa, my voice came back. You can find this by solving kcat, k uncat and dividing them, or you can figure it out based on delta G, or you could do one thing, which is no kcat, k uncat, and then solve for what delta G is, right? If you know rate acceleration, that also equals this. And so you can know these two and then figure out delta delta G. Yeah. What'd you ask, Sydney?
So when it comes to the efficiency equation, how would we solve for Ki?
You'd have to use a Lineweaver-Burke plot, right? The Lineweaver is kind of a key piece of a lot of these equations. And so it's very likely that you're going to run into a situation where you need to have a Lineweaver to solve a bunch of this stuff. Because these are all experimentally determined. These other things we can figure out, but we have to go through those to get there.
So how would we find K uncapped?
So you'd have to measure the rate, right? And then we get into our final big equation. This is the other heavy hitter of this unit.
K as in big K or
Little k. So rate constant k, which is a little k. So for example, if you measured the rate of the uncatalyzed reaction, figured out the rate constant from that, then you could know k uncat. If you were, you can do that one way, or you can know the delta G naught double dagger, and then solve for k uncat.
So that is K for the rate constant.
Yep.
Which would be the uncat because that's not including any enzyme.
Yep.
Which also gives you a K uncat.
And a couple last ones before we start working on some stuff. Rate equals K times concentration of A. If we had an example of a reaction going A to B, the rate only depends on, number one, what the rate constant is. So that would include things like steric hindrance, other things that might slow down the reaction, as well as how much A we have to start with. SN1 or S, this would actually be like more like an SN1. It's first order. Most things are first order when it comes to like K-cats.
Okay.
And this is called the differential rate law. If we had an SN2, we'd have to multiply it by both reactants.
Okay.
Yep.
So what is differential?
Yep. And if it's uncatalyzed, you would use that one.
What does differential mean?
Differential means so like a derivative is like a change over time, right? So if you figured out what the derivative of a line is, you know what the slope of the line is at a given time. So this would be how fast does A change over time? You could write that as a d A dt, the change in A over time. So that's going to go down, and that would be our rate. How much is A going down over time? That's what a differential is, right? And then we also have the integrated rate law. A at time t is equal to A at time 0, e to the negative kt. Which tells us how much of A is left, given how much we started with, how much time has passed, and the rate constant. Yep. You got it. Yep. These are all little k's. Where are the big k's here? Can you find them? Okay. We have one here, Km. And then KEQ we had up here just a minute ago. Those are really, and then we have KDs. We'll talk about all our Ks here in a minute. Okay? Okay. Again, on an exam, I will be clear about which one is which. I know my writing isn't always 100% clear about which one is which, but context should tell you a little bit about which ones are which. Yeah? You got it. Okay, other ones that are on our sheets. I have an annotated sheet up right now that kind of talks about all these again, that you can kind of have a reference to. Alpha is not. Alpha is the inhibition factor from an inhibitor. KD for the inhibitor. I also will call that KI sometimes. The inhibition, KEQ. And KD is always a large K.
So KI equals KDI.
Yep.
And then what was the difference between the competitive and non-competitive?
Yep. So what happens with the competitive inhibitor? What changes? Competitive competes at the active site, right? So what is it screwing up? If you're competing at the active site, you're screwing up Km. How do you screw up Km? Does it go up or down? Remember that Km is a kind of KD. KDs are dissociation constants. So if you want to screw this up, you want to make it dissociate more, right? Make it fall apart more. And so competitives are going to increase the Km and screw up no Vmax, right? All they do is block the active site, like the black beads that we were pulling out of our little activity, right? Every time you pulled a black bead, it didn't count, right? So same thing here. Didn't do make products. All it did is take up the spot in your fingers that normally would have been grabbing red beads, right? And so in this case, Km apparent, which means Km with an inhibitor around, is equal to Km times alpha. It's always going to be increasing by some factor greater than 1.
And that would make sense because if we increased KM with the efficiency would go down.
Correct, because you're going to be dividing by a bigger number.
Right.
Likewise, for non-competitive, what happens with non-competitive inhibitors? Where are they binding to? Are they binding in the active site?
No.
Typically not. They're binding in an allosteric site, which is a second site on the protein. So what they do is they lower Vmax, but really it's by lowering kcat, making it essentially bringing that barrier higher, right? By introducing some extra sterics or making it hard for the enzyme to do those changes, it makes it harder to get over that barrier, and so therefore it slows down the enzyme. Okay, so in this case, Vmax apparent is equal to Vmax over alpha, always dividing by something 1 or greater. Little k's are rate constants, big k's are equilibrium constants.
KCAT is an equilibrium.
Kcat is not.
Oh.
And all big K,
That meant KQ.
yes, all KEQs are made out of little k's. So big k's are often made out of little k's. I've tried to draw them smaller and larger here. And so you can always use that identity to also get places and connect ideas. Make sense? So hopefully we've covered all the k's and all the major equations here. Okay. Well, let's have some fun then.
Will those non-competitive and competitive equations be on the front?
I gave you the literal front sheet of my exam. It is posted on D2L. Yep. Yep. So
Oh, yeah, you did. Okay.
that is exactly the cover sheet of the exam.
I think you put it on the quiz too.
Yep. And that the quiz one may not be exactly the same as that exam. So again, know that. If there's things up here that we've talked about that aren't on that sheet, that's stuff you're responsible for knowing off the top of your head. But almost all of these are on that sheet. I think the only ones I don't specifically have on there is like this one. You should know that much at least. Definitely.
Will you have all this writing on there too?
No.
Okay, I was gonna say.
That's annotated so you guys know how to study for it.
Okay.
The real one is going to be just a regular old cover sheet. That one.
Can we just...
Okay, I'm going to do a multi-part question here. So part one of this question. Make it irreversible. I'm going to start writing my little k's with curly k's. So maybe that'll help you see the small ones. A reaction of 15 millimolar R is set up. After 13.2 minutes, 7.1 millimolar is left. What is K?
Would we start use the differential law, or would we do it differently?
Good question. That's exactly what I'm asking you here. What do we use here? So let's go through this, and I'm going to work on decoding all the things into actual variables, and then maybe we can use those variables to kind of stick it back together. Okay? So a reaction of 15 millimolar R is set up. Do we have a variable here? Some sort of a thing we can plug in? 15 looks like a thing. What does that correlate to? Concentration of R. Okay, I see that. What kind of concentration of R is that? Initial. So R at time 0. Right? So we know that that's how it was set up. 13.2 minutes. Time. What's that? Sure. Time, in this case, it would be in per second. 7.1 millimolar. R at time 13.2 minutes. So we had R0, T, and 13.2 time R at 13.2. Which equation are we going to use?
Integrated.
Yep, integrated. Which is R at time 0, or sorry, R at time 13.2 equals R at time 0, e to the negative k t. So we're going to plug in here, 7.1 is equal to 15 e to the negative k. That's what I'm asking here. That's going to look like ours. I can't win. Whatever. I give up. Okay. What is our T? 792 seconds. Yep. All right. (9.444 times 10 to the negative fourth per second).
And that is K, that's a rate.
It's a rate constant K. Is this catalyzed or uncatalyzed? Yep, it's in free solution. Doesn't say anything about an enzyme or catalyst. So this would be a K uncat. Yeah? See how to do those? Okay, part 2. An enzyme is capable of lowering the energy of activation of this enzyme or this reaction by 12.2 kcals per mole. What is kcat?
Okay, so would this be delta G thing?
Okay, so let's go through it. Lowering the activation energy by 12.2 kcals per mole. Okay, so this is negative 12.2 kcals per mole. And what's the variable there?
Delta G.
Yep. Activation energy is talking about transition states. So this would be a delta G, not double dagger.
Can we use the K equals the E?
So there's only one equation where this shows up. Literally the only one that has this in it. If you know it, you know it. If you don't, you don't. Which equation has delta G, not double dagger in it? Okay. Kcat over K uncat. What is that called again? What's the other word for this? Rate acceleration. So what's the strategy here? We know delta G, not double dagger, so we can plug that in here. We can solve for rate acceleration. We also know K uncat. So if we know rate acceleration times K uncat is going to give us kcat. Right, I didn't say the word acceleration here, but you had to pull out that this is lowering the activation energy, which is a delta G, not double dagger, which means this equation needs to be used, and we can use this equality to figure out kcat. Yeah. If I don't say it, what do we assume? 310. Unless I specifically say something else. What's that?
So R2 is 6.6.
Correct. So negative 12.2 over 0.616. Because it's negative here and it's negative there, right? Don't drop a negative. Remember that rate acceleration should always be greater than 1. If it is ever less than 1, you messed up. Because enzymes don't slow things down, right? If that's ever less than 1, you probably forgot one of these negative signs. Okay, so 12.2 divided by 0.616, e to the x, 3.993 times 10 to the 8th is our rate acceleration. We done? Now we need to find kcat. And this equals kcat over k uncat. And our k uncat we have a value for, right? 9.444 times 10 to the negative 4th. What's kcat? What?
3.769 times 10 to the 5th. Oh, you just need to have it in. No, I switched mine back and forth.
There's no units on that?
It is per second.
Remember? Wait.
All small k's are 1 over seconds. Unless I specifically asked for it, I'm not taking points off. Yes, I'm hardcore about this. 1 knuckle at a time for every unit. Yeah, you can go with 4 fingers.
Isn't your thumb one of the really important fingers?
That's the most important, I think.
Yeah.
It's like what sets mammals apart from other species or primates.
It's like the big toe is the most important.
True facts. Yeah. All right, part 3.
Oh, the universe.
Yeah.
And stuff.
The enzyme is known to bind R with an affinity of 22 millimolar. If 0.2 nanomolar of enzyme is mixed with 13 millimolar of R, what is the velocity?
That is the one with the substrate over
Well, let's go through and pick out our things, right? That's what we should always do in this. If you ever have a question on how to start these, decode them. Put them into the right symbols, right? What? 13 millimolar?
and that's 0.2 nanomolar.
It belongs in a museum. Okay, so what do we got? Enzyme is known to bind R with an affinity of 22 millimolar. There's a number, so it's got to have a symbol for it. An affinity of 22 millimolar. The enzyme is known to bind R with an affinity of 22 millimolar. Oh no. 22 millimolar. What is this?
Is it the substrate over K plus substrate?
One thing that this could possibly be, enzyme affinity for substrate. That's why you're here. Km is the affinity of an enzyme for its substrate. If we're talking enzymes, the word affinity only typically will mean Km. Yep. Okay. 0.2 nanomolar of enzyme. Here's another number. This is E total. Okay, it's mixed with 13 millimolar of R. Here's a new one.
That's
Substrate. What is the velocity? Okay, so which equation has V naught, Km, S, and E total in it?
the V max times S over Km plus S.
I think you're saying this.
How do we know if velocity V is 0?
And this is typically that's what it will always be, unless it says V, the maximal velocity or something. Okay, can we expand this farther? Because I don't see a K cat. I don't see E total.
Times E.
So how do we expand this more? Okay, K cat times E total is V max. There we go. So there's all of our things have incorporated. E total's there, S is there, Km is there, and V naught is there. We have nothing that's hidden, right? You might get to this point and get stuck because I don't know where V max is. And you would have looked and say, oh, there's E total. I need to use that form of the Michaelis-Menten equation. Okay, so we can plug in. Do we know our K cat?
From the last equation.
Last one?
3.769.
What's our E total? Is 0.2 nanomolar. Okay, and then our S plus Cam plus S, 22 millimolar, 13 on the top.
22 plus 13 on bottom.
One thing you might want to watch out for here is make sure the units are the same. They have to be the same inside of here. They do not have to be the same outside of there, because they won't add together if they're not the same units. And when they're the same units like this, then they become unitless, and then the units for velocity are just whatever you have outside here. Okay, so number one, what's the fraction bound here?
It's 3.714 times 10 to the negative
0.3714. So we're 37% of Vmax here. That's what this whole thing is. What is Vmax? Units, nanomolar per second, times 0.3714. Well, we have to figure that out, shouldn't we?
Well, a good enzyme is
Sydney? So I multiplied kcat times E total to get Vmax. I solved the fraction bound to get this number, multiply them together to get initial velocity, and that's what we got.
Oh, oops. Yeah, I accidentally put 4 on the 7.3. What the heck?
Taylor. Make sense, guys? So Matt was asking, is this a good enzyme? Is it? How would we know? Is this a good enzyme? I can get some smart aleck answers here, like nothing's perfect. But the biochemistry gives us a range of perfection, right, Sydney? Yep, 10 to the 8th to 10 to the 9th per molar per second. So how do we know? How do we know if this is a perfect enzyme or not? You guys might have remembered this trivia question of what makes something a perfect enzyme, but how do we actually figure out if this one is one? What's the enzyme test for perfection? Efficiency, which is kcat over km. Got our kcat, which is what, the 3.769. And our km is 22 millimolar. Remember to convert that to molar. Is this a perfect enzyme? Missed it by a factor of 10. It's close, but no cigar. But again, you don't have to be perfect. A lot of enzymes are good and just fine 10 to the 4th. Yeah, you're not that good. I want to figure out all your guys' K-cats over KMs. 0.4.
So would you say not quite?
Yep, I'd say no. Is this a perfect enzyme? Nope. You need to be 10 to the 8th to 10 to the 9th. If you ain't there, you ain't perfect. Yep. Maybe it needs to evolve a little bit more. That's pretty much, we've never seen one bigger than that. What's that? Yeah, I guess that's where you would naturally come to from this, is that Pluto's not a planet. Micah. Missed it by that much. It's a dwarf enzyme.
So now we can conclude that.
Okay. Yeah, that was the big takeaway from this. All right, so you guys see how these can all link together?
Yes.
I will tell you there's going to be multi-part questions like this. Now, when I grade those, I will give you credit for if you carry that answer correctly into the next part and you're doing multiple parts right with the wrong numbers. If as long as you did them right, they'll be correct. So like screwing up in part 1 is not going to screw you for 7 other parts of the question, right? But it will screw you up on part 1, but it won't screw you up on 2, 3, 4 through 10 or whatever, okay? As long as you're doing everything right with the wrong numbers. -2, Taylor. I took off points from you.
Oh.
What next? Oh, sorry. We did all the equations, all the K's. We did some rate laws there, right?
Yeah, we did. No, we didn't do a ton. I want to do the graph stuff with the determining what is what in the graphs when there's multiple bumps.
All right. Let's do it then. You want multiple, you want the like the delta G stuff with the bumps and all the, okay.
Yeah, that is stuff. Which one is yeah.
I don't see any big K's up here, do you? Need to work on your intuition.
So I can't really tell which one is K cat. I would maybe think K.
There's only one way to know, and that'd be look at the numbers. How would you know which one's going to be K-cat? Which will be rate determining overall?
The highest.
The highest bump total. Okay, I can't really see that because I'm not drawn to scale here, but the highest bump is going to be the lowest value for K. 120.3 per second. K negative 2 is 0.073 per second. Yup.
Yes, this is what I really need.
Okay. Let's do some stuff. So there's some easy ones, some not so easy ones here. Might as well pick the low-hanging fruit while it's just low. It's the easiest one of these 5 things to solve. Well, one thing we can't do yet, this one needs to come after k negative 1 and negative 2, so we can see which one has the smallest value overall. Okay. We can figure out one of those two pretty quickly. And then one of these transition state energies is pretty easy, the other one's pretty hard. Okay, you're on the right track. Okay, Hattie, what are you saying? So this thing, k2 over k negative 2 equals something. What are 2 little k's combined to make? A big K. Okay, this would be KEQ from S to T. Right? And we can get to KEQ from S to T from delta G naught from S to T. Right? So the first thing we're going to need to do is find KEQ for S to T. And then we're going to need to find K2 after that, because we know K negative 2. Okay, so let's first find KEQ. So delta G naught is equal to negative RT ln of KEQ, correct? And if we want this one, we're going to do S to T. That'll be KEQ S to T. So we have 7. What temperature are we doing? 310. So negative 0.616. KEQ is E to the negative delta G naught over RT. You've probably seen, actually I know you've seen that about 13 times today already, right? In different forms, delta G is in there, delta G naughts, double dagger, right? Essentially all these equations boil down to the same stupid equation. Delta G is negative RT ln of KEQ. Okay, so we're negative E to the negative 7 over 0.616. KEQ from S to T. So I got KEQ S to T to be, what'd you guys get? And that equals K2 over K negative 2. We know K negative 2 is 0.073. Right? So then K2 is, Sydney? You followed me on that part, right? You got this number as well? KEQ is equal to 1.16 times 10 to the negative 5th. You got that much? Okay, and remember KEQs are made out of a forward over reverse rate constant for the step. So I plugged in my value for K negative 2, which was given to me in the question. And now I'm just solving for K2. So K2 is going to be 1.16 times 10 to the negative 5th times 0.073. What is K2? Ta-da! So I'm going to write that in here in red. Yep. This became a KEQ, and the KEQ allowed us to convert between the forward and the reverse rate constants. 10 to the negative 7th. I'd probably be willing to put money that that's going to be our KCat, because it's pretty damn small. right? Unless this one is even smaller. So we need to figure that out too. Okay,
Well, what if you're asking for the forward or the reverse?
check. That one's done. Yep.
So they can solve the delta G not double dagger or not dagger for 2.
Yep, we can. We know that. Now we can find delta G naught double dagger 2.
Would that be the next logical step? Or should we
Yep.
say now?
Why not? I don't think there's any necessary logical progression through these. If you wanted to do all of these first and then all these last, cool. If you wanted to do the two that are connected here, cool. It doesn't really matter. You just got to get them all done. So I think the obvious thing now is, now that we know how tall this barrier is, why don't we figure it out in energy terms? How tall is that barrier? Okay, so what do? How do we convert between a rate constant K and a free energy K? Arrhenius equation? We're going to be plugging in our K negative 2 right here. Always little k for this. Okay, we have values for kBt over h given before. Do you guys remember what the standard value for this is? What is that at what temperature? Are we working 298 here? Nope, so we're going to need to scale that up. Okay. Remember to scale this value. Since it's already times h, or sorry, already times t, we're going to put the value we want over the value we have, and that'll scale it up above. So I think it's like 6.48 times 10 to the 12th. If we chilled it down, went to 0 Celsius or something, then it'd be 273.15 on the top over 298.15 on the bottom. Right? That's how you can scale that value. Okay. So we have K negative 2, it's 8.475 times 10 to the negative 7th equals K2, right?
Yeah.
This number? We're using the same number here because we want this height, and that one correlates to that height. Ooh, K2. Yep, K2. Yep. So first thing I'm going to do is divide through by that big number, the 6.48 times 10 to the 12th. How do I undo the E? Natural log it. Yep. Free energy barrier is 26.78 kcals per mole. Make sense? Do you see how I did that? Now's your chance to get your questions answered on that.
When I did the natural log, I got so I did the natural log, that's why. Never mind.
I won't mind it. What would the height of the other transition state barrier be?
What did it be?
Pat? How would you know? So you plug this in and solve for that. Another easy way to do that would be to know this number and then apply the 7 to it, right? Because you know these are different by 7. You're just going to take this one minus 7, and that's going to make this shorter, so 19.78. Right? These all add together. This part plus this part is going to equal the whole height. So there's always multiple ways to solve this. If you had this one, solved it, then you can figure this out really easy without having to solve K2. Of course, here we needed K2 as well, so whichever way you want to go about it. There's lots of pathways to the right answer here. You just have to find them. Nate?
So what does the 19.78 equal?
That would be the delta G naught for the reverse of 2, like going over this hump instead of going this way. Should be easier to do it this way than to go the other way. Make sense? All right, so we got that.
Now we did find delta G. I'm sorry, I missed that. What did we find besides that?
If we were asked for the reverse here, then it would just be what the 7 plus 19.78 equals this. That's what Pat did, yep. So what he could have done was solve this, added the 7 onto it, and then he would have had this whole thing. Right? You can get the same answer in multiple different ways. Since energies are all additive in state functions, it doesn't matter how you get there. You just got to figure it out. Okay, what are we still missing? We're missing K-1 and the free energy barrier going forward. Now this is where it gets a little bit more tricky.
So should we solve for K-cat then? When we use K-cat aside?
We won't know K-cat until we know all values of K, because it's the smallest one. So if you want to find K-cat, we'll need to find K-1. So we have one of the K's, but we don't have the other one. So how can we figure it out? We'll need a KEQ. Okay, I agree with that. K1 over K-1 is going to be KEQ for R to S. Last time we did the exact same thing, but we had a delta G value, right? So now we need a delta G value, but we don't have one. How can we find out that delta G from R to S? What are some stuff that we haven't used yet up here? The overall, that's from R to T. So what if we said the delta G from R to S plus the delta G from S to T is equal to the delta G from R to T? Would you agree with that statement? If you add this one plus that one, that's going to equal the whole thing. We have some of those values, right? We have S to T is what? What's the delta G from S to T? 7. The overall is negative 0.3. So what is R to S? Yeah. 7 is given in the question. We're also given the overall. What's that? Yep. Yep, so now we can find KEQ for R to S. So all these little mathematical kung fu moves, we have to stitch them together to answer all this. You have to know how to navigate your way around this. You have to know that delta G's are additive, right? And that's one way we could get an unknown delta G. Okay, so KEQ again is e to the negative 7.3 over 0.616. Negative, negative. We got 1.402 times 10 to the 5th. Yep, and we know K1, 120.3 over K negative 1.
So I'd say that the K
You guys get that same number?
cat is K2.
Check. Do we also know K cat? We have all 4 of our K's solved out now. Which one is the rate determining step? K2. The smallest one possible. Yep.
So your rate determining step can be any of the 4 Ks.
Mm-hmm.
That's the other answer.
Yep. The slowest step possible is going to tell you how fast you can go. Does that make some sense, folks? We all done?
Now we need to find out.
We still need to find the first delta G, right? So what do we need to plug in? Which K are we going to use? We have all 4 of them now.
I would say K1.
K1, the one that is correlated to the same height.
Is that the one with the 6? Yeah.
Ta-da! Yeah?
That got a lot of good stuff.
Okay, what would be the height of the transition state in the reverse direction? How do I find this height? Again, we can use the same trick that Pat used just a minute ago. Do we know what this depth is? The R to S delta G. It's negative, what, 7.3?
Just add that.
Yep. So it would be what, 22.52?
I forgot why we needed the part of S.
Why we needed it? Because that's what gave us our delta G, so we could find the KEQ to find the other one. Right? So in the reverse direction, what's one's K cat? 19.78 the first step. K negative 1 is 22.52. K negative 1 would be our K cat in the reverse direction. In the forward direction would be K2, our rate determining step. Yeah? So if you were an enzyme in the forward direction, where would you want to do most of your work? Which rate constant would you want to lower the most? Yep. If you wanted to go forward as an enzyme, you'd want to lower this transition barrier. If you were going in the reverse direction, you would want to lower this barrier. Right? You always work on K-cat. That's how enzymes work, is by lowering the rate energy of the rate determining step.
Are there any practice problems when you practice that?
Yeah, I have so many practice problems for this unit. The rate constant practice problems, the kinetic practice problems. Yes. The rate constant problems are the ones you want to do for this. This is exactly what that, if you can do the rate constant practice problems, you'll be in excellent shape for the exam. It makes you do physically everything you could possibly be asked to do. Does that make sense, guys? How to do this? How to do to work your kung fu magic to kind of get between the things, interconverts, figure out relationships. The different constants are always linked by KEQs, and you can either be given those KEQs or you can have to solve for them from a delta G, right? Heights of transition states only depend on the rate constants. So like these ones, we just needed to know the correct rate constant K to use to find them. And then delta G's are always additive.
So on an exam, would you give us a graph like that, or would you expect us to draw it out?
The practice exam has one exactly like this on there. And it says to decorate and give all missing values.
Okay.
We can, like, I guess, like in my head, like, you can give us a question that's like, decorate this, and everything's missing. Because you need keys to solve the other stuff.
If I give you and everything's missing, yeah, the decorations I'm going to get are like smiley faces and stupid. Yeah, I have to give you enough to work with. But like this one, I only gave you like, what, 4 values total?
Yeah, but you need to give us something.
Yep. I need to be able to give you, for example, I gave you this piece, the overall, and 2 rate constants. And then you had to be able to figure everything else out from there. Yeah, here's an empty graph. Give me some stuff. Yep. Does that make sense, guys? Questions on this, please? This stuff is the most complicated stuff on this exam. Everything else is really straightforward, I feel. Pat? You can't. Yep. You cannot change the physical energy level of a molecule, right? Bonds are still stuck together in the same way if an enzyme's there or not, right? And that's really what these G knots are telling you. Is this one higher or lower in energy? And enzymes can't physically change that. They can just change the pathway through the mountains to get there. It shouldn't be. It shouldn't be. Because there's no one size fits all for this whole thing that correlates just to this. Right? Because the delta G's are not connected to delta G not double daggers. The rate constants are connected to the double dagger. This just only tells you a little about the general energy stacking. But it changes them evenly on both sides, right? So when you lower this energy, it's going to lower both rate constants the same. So KEQ is always still going to be the same. Because it lowers it by the same factor. Right? So if you change this K, you change that K too, and KEQ is unchanged. Because it's even on both sides. It speeds up both the forward and reverse reactions equally. Never. Never. Yep. So if this is, for example, an enzyme binding to something, then yes, R to S would be a KD.
Okay.
But I didn't say anything about an enzyme here, so we're just going to assume this is just free solution chemistries.
Okay.
Yeah? Do you feel comfortable doing that kind of stuff? Or more comfortable? Okay. Okay, what is the catalytic efficiency of this enzyme? Okay, so Taylor nailed the first part of this. Translating catalytic efficiency into its variable terms. What is catalytic efficiency? K cat over Km. We do. We need to figure out the smallest value possible for K. Okay, we also need to figure out how to write Km for this equation. Yep. Yep. Products over reactants. How do we find Km? That is a good question. We'll get there. Perhaps. Cannot guarantee that the actual diagram is going to match what we see here. For example, 37 8,401 EPs over 1 ES. How would I correct this graph to make it look more correct? If we have 37,000 enzyme plus products for every 1 ES complex. Are you going to have 37 at the top of the mountain? 37,841 and then versus every 1 at the bottom of the mountain? No, it's going to be different than this, right? It's actually, it should be like this. It's going to go through the floor. Yep, so E plus P actually should be way down here. So our KEQ really should correlate to this. Exactly. Absolutely. That's one reason I do that. So we're going downhill here. Okay, so we have two problems here. We need to find K-cat. And how do we find K-cat here?
Which is the smallest case?
Smallest K value is our K-cat, right? And then Km, we'll have to figure it out based on the rate constants too. Okay, so what do we want to do first? Solve for Ks? All right, which one's easiest? K1? All right. I don't think so. I think we have a KEQ already here. And we can just set that equal to K2 over K negative 2. Right? Because of KEQ, we don't even have to take it out of delta G. We can just plug straight in. We have 37, 841 equals K2 over 4.7 times 10 to the 2. So what is K2? That does not look like much of a K-cat to me. Though it could be, depending on what the front one is. Okay, now we want to solve for K1. How do we do that? Well, we're going to make this into a KEQ first. KEQ is negative delta G over RT. E to the negative delta G over RT. KEQ is 15.8 here. And that's an equal K1 over 4.4 times 10 to the negative fourth.
So K cat is actually K2.
K cat is what?
Is
The lowest value for K.
I thought it was negative 7. Oops.
K1 is our K cat, right? In the forward direction.
K1 is.
Right? In the forward direction, this is our K cat. In the reverse direction, this is obviously a K cat in the reverse direction. Okay. Do you see that? So since E plus S goes to ES, the enzyme catalytic efficiency in the forward direction would be here. Okay? So K cat is 6.95 times 10 to the negative 3. All right, so how do we find Km?
I just remember finding KM on the graphs.
All right. So let's write this out. Ways to make over ways to break. Or, sorry, ways to break over make. Because remember, Km is a type of Kd, breaks over makes. And we're talking about ES. Because ES controls the products we make. Can't have it without going through the middleman. So now we need to know which ones are reversible and which ones are irreversible. So if there's greater than a factor of like 100 between them, it would be an irreversible step. So for example, these ones would be reversible because there's only a factor of 10 between them or so. You see a 10 to the negative 3 versus 10 to the negative fourth. In fact, it's a factor of 15.8. So this would be a reversible step. What about this one? Reversible or irreversible? Irreversible, right? We couldn't get back out of this thing. Right? There's a factor of 5 here. In fact, a factor of what? 37,841 between them. That's greater than a factor of 100. So typically that would be an irreversible step. So how do we define a Km for this? How do we break up the ES complex? If you wanted to break this thing up, what are your choices? K2 is 1 or K negative 1. Remember that when we're talking about logic here, addition means or. So you could either go this way or that way, so we add them. When we're talking or logic. How do I make the ES complex? Just K1. Okay, so let's solve Km. Yep.
Times 10 to the 9. So
This is real bad. Why is this so bad? Well, if you're this enzyme, what are you going to spend the most of your time doing?
Getting them over K1.
Well, it's going to be hard to get over this bump. And once you get there, it's just going to be immediate products, right? So it's super easy to break this thing up by going to products. But it's really, really hard to gain them, right? Because these barriers are really, really high. So it's super hard to bind your substrate. And you also can't do many reactions because Kcat is also part of that binding, right? And so this is a just awful enzyme. 10 to the negative 12th? Remember, we want to be 10 to the positive 8th. So we're like a factor of 20-fold worse than perfect here. 20 orders of magnitude worse than perfect, which is enormously bad. This is molar. You always tag a molar onto it. Yep, anytime you solve a big K, it's always in molar. So I made this, what, 10 to the 9th, like 1,000 megamolar. I don't know what the 10 to the 9th is. Yep. Gigamolar. Yeah, there you go.